Assalamualaikum warahmatullahi wabarakatuh. My name is Amna Batrisha binti Azali. Today, our group will present to you about Howe Bridge. So, Howe truss, a unique structural design that has revolutionized the construction industry, is developed by William Howe. The truss system is renowned for its exceptional strength and stability, making it an invaluable asset for spanning long distance while using minimal materials. We will examine the innovative ideas and engineering principles that led to the creation of the Howe truss. We will also analyze famous structures like the Brooklyn Bridge that use this design, exploring its practical application and engineering significance in the architectural landscape.
Background of case study. The background of case study about the Howe Bridge could encompass its historical significance, structural feature, and its impact on transportation and infrastructure development. It may delve into its construction, material use, and the engineering principle behind its design. Additionally, it could explore its contribution to local communities, economic development, and to the evolution of bridge engineering practice.
And hi everyone, my name is Aliosna. So today I'm going to explain about basic theory of Howe truss. So Howe trusses are essentially the opposite of Pratt trusses in terms of geometry. In fact, looking at a Pratt truss upside down will visualize a Howe truss of sorts. The entire structure is still relatively the same, but the diagonal braces are now occupying the opposite or the unoccupied joints. This switch in position of the diagonal members has a very important effect structurally. For Howe trusses, the reverse becomes true as diagonal members are now in compression, while the vertical loads are in tension. As they are similar in structure to Pratt trusses, their uses are generally the same. To maximize the efficiency of the truss can be loaded at the joints of the bottom chord.
So, for the real engineering application, first, Howe truss have been widely used in various engineering applications, particularly in the highway bridge. Second, Howe truss bridge design efficiently distribute the load, making it suitable for highway where wide spans are often required. Third, Howe bridges are designed to use material efficiently, minimizing the amount of material required while maintaining structural integrity. Fourth, Howe truss design can be adapted to the different environmental conditions, including seismic activity.
Okay, so right now I'm gonna give an example of calculation for Howe truss bridge. So based on the diagram below, the Howe bridge truss is subjected to the loading shown. Determine the forces in members FD, DG, EG, and state if the members are in tension or compression. So based on the question, we need to find the force for members FD, DG, EG, and also we need to define whether it's tension or compression. So how do we want to know if it's tension or compression? So if the amount that we get is positive, so it's tension, and also if it's negative, it is compression. So here are the solution for the previous question. So I'm going to explain it to you guys step by step. So let's start. So the first step is to find the total moment for joint A. So why we find that first? Because it has the less unknown, which is only one, that is HY. So formula for total moment for moment is M equal to FD, which is moment equal to force times with perpendicular distance of force from point of interest. So let's say if the force given is at y-axis, so we need to take the perpendicular distance which is at x-axis, and if the force is at x-axis, we need to take the distance at y-axis. So for this question, the total moment for A is equal to 0. So 0 equal to force 0 equal to negative 10 times hy. So why is it negative 10? Because it rotates anti-clockwise. So the distance is -10, and also the force is Hy. So that's why -10 times Hy, and then we add with 3.6 kilonewton, which is the force at joint F, times with the distance, which is 7.5 meter, and then plus with 2.5 kilonewton, which is the force at joint D, and then times with the distance 5 meter, plus with 2.9 kilonewton, the force at joint B, and times with the distance 2.5 meter. So we're gonna get Hy equal to 4.675 kilonewton. And then the next step is to find the total force for y-axis. So total force for y-axis is equal to 0, and then 0 equal to ay minus with 2.9. So it is negative because the force go downwards, and if the force go up, it's positive. So ay minus 2.9 kilonewton minus 2.5 kilonewton minus 3.6 kilonewton, and then plus with the Hy, which we just count just now, that is 4.675 kilonewton. So we're gonna get ay equal to 4.325 kilonewton. And then the next step is to find the total force for x-axis, which is equal to 0. So the only force for x-axis here is ax, so that's why ax equal to 0. And then the picture below is FBD, which is free body diagram for point G. And then since we already count for the unknown, now we can find what does the question want, which is the forces at FD, DG, and also EG. So the first one, we find the force for HG. So we need to use the total moment at point G equal to 0. So 0 equal to dF times with the distance 2.5 meter minus with 4.675 kilonewton times with 2.5 meter. So we're gonna get Hg equal to 4.675 kilonewton. It's actually negative. So if it's negative, and then we will know that Hg is compression. And then the next one is to find the total force for y-axis. So for this one is for point G. So total force for y-axis is equal to 0, and then 0 equal to 4.675 minus with 3.6, and then minus with dg sine 45. So here we got angle for dg, so that's why we need why is it sine? Because it's opposite opposite of the angle, so that's why dg sine with 45. So we're gonna get dg equal to 1.52 kilonewton, which is negative 1.52 kilonewton. So if it's negative, and it's compression. And lastly, we need to find the total force for x-axis equal to 0. So 0 equal to 4.675 plus with 1.52 cos 45 minus with EG. So why we use cos? Because it's adjacent beside with the angle. So we're gonna get EG equal to 5.75 kilonewton, which is positive, so it's tension.
Hello everyone, my name is Vidya Sridevi. I'm going to give a conclusion behind this entire project. We know that the Howe Truss Bridge rocked the bridge building world during the 80s and early 90s. It was a game changer because it uses a mix of wood and iron to make a super strong bridge. Picture this, it has an axe-shaped design, kind of like a big sturdy puzzle piece. Back then, it was the superstar of bridges connecting different places around the USA. Even though we got fancier bridge tricks up our sleeves now, these bridges were a big deal in their time. They were tough and big, flexible, which made them perfect for helping people and stuff travel around the country. Today, you won't even find lots of these bridges hanging around, but the ones that still stand are like awesome time machines. They are like cool reminders of how genuine people were when they built stuff back then. These bridges tell us a story about how they helped build the roads and connections we rely on today. They are like old school superheroes that keep on inspiring us even though they are not as common anymore. I hope you guys understand what I had presented, and that's all from my part.